So this is where we left off after the last video. We had created a basic particle system that creates one new particle each frame of animation, emitting from a central location with a random velocity. We identified a pretty major issue in that we don't have any mechanism to remove particles. We add them to the list once every frame, but even when they're off the screen, we're still calculating and trying to draw them, even though they're not being represented. And this causes a pretty noticeable performance hit early on, and eventually if we run this long enough we'll exceed the amount of memory allocated for processing, and we'll probably just see a crash. So that's one of our main jobs in this video, is to look at building some logic into our program that'll help us manage the particles when they're off the screen, or some sort of strategy to remove them after a set amount of time. Also, we'll add a little bit of basic transformation capabilities to make maybe the motion of the particles a little bit more interesting. So if we look at our particle class, we clearly need to add a few extra properties. Right off the bat, I would create a Boolean variable called alive, and this will just be a flag that lets us know whether or not a particle is still active. So we'll initialize it to true. When we make a new particle, we're going to assume that we want to keep drawing and moving it for some amount of time. Now, there are a number of strategies we could use to decide when a particle is no longer alive. One logical one would be when it goes off the side of the screen. Another one could just be if it's existed for a certain set amount of frames. And I think that's what we'll use in this example. Next, we'll make a variable called lifetime. I'm putting this in capital letters because this is what we would call a constant variable. We have no intention of changing it once the program has started. It's just going to store that set number 100, and we'll use it for comparison reasons. Lastly, let's make a variable called steps, and this is going to track how many frames this specific particle has been alive for. When we initialize the particle, steps would be equal to 0. Now, our move and our display functions are called once per frame. So we could actually add this logic sort of into either, but for me I think it makes a little bit more sense to put it in our move function. Whenever our move function is called, clearly we've moved one more time, so we could increment our counter of how many frames I've been alive for. And then I also could do a check to see if the number of steps this particle has taken, or moves it has taken, is larger than our lifetime value. This would be where we could possibly change that Boolean variable depending on how many steps we've been around for. So let's build a basic condition. We can say if the value of steps is larger than our lifetime, sort of the number of allowable steps, then I'm just going to set alive to be equal to false. We also want our outside programs to have access to this variable, so we should create one more function, and we're going to say it is a Boolean return type, and let's call the function isAlive, and just a very simple return of our alive variable. So if from the main function on a particle we say .isAlive, that's just going to return whatever the current value of that alive variable is. Now if we go back to our main function, we don't actually have to do very much. Right now we're still moving, we're still displaying, but we need to do a check to see, is this particle still alive or not? And we might even want to do that before we move and draw it. Officially, if it's dead, we should just be pulling it out of our array list and not wasting a step of moving and displaying it. So one more condition is what we need. We can say if particles.get at position I, so that's the current particle that we're looking at, and then let's access that isAlive function, right? And this is going to return true or false. We're interested in the case where it's false. If particles.get.isAlive is equal to false, then we simply want to remove this current particle from our array list, and we can do that by using the remove function, and we're just saying remove whatever is at element I. And if we were to run that function, we should see now that after 100 steps our particles start disappearing. And so it gives us a limited scope in terms of how far they're able to travel before they expire. And we could change this to a number of different values, and it's going to change the visual output of the program, right? If we have a short lifetime value, they won't be moving very far. If we say lifetime is equal to 200, we're going to see that they're going to get a little bit closer to the edges of the screen. Okay, we'll put that back to 100. For the second half of this video, I'd like to look at some of the basic transformations that we can use with the translate, rotate, and scale functions. Now, these functions actually don't apply to objects themselves, but actually transform the whole coordinate system, which actually is a pretty powerful capability that we can use in processing to make all sorts of visual effects quite easily. The key for us is that we can actually create different coordinate systems sort of stacked on top of each other with the push and pop matrix functions. If I were to write push matrix before I have my rect function here, and then I'll put pop matrix behind it, the code in between is executed on a totally separate coordinate system than the original one. Right now it actually is, it would be an identical copy because we haven't used translate, rotate, or scale, but it only exists for the amount of time between when we push it and when we pop it. Basically it adds one onto memory and then it pulls it off when we're done. Now if we can actually use translate, which moves the origin of our coordinate system. So if we say translate and we were to move the origin by location.x and location.y, that's going to actually move the origin to where the rectangle should be. So we actually could draw the rectangle then at the origin at 0, 0. And if we run this, we're going to see that it basically has the identical behavior as what we had before. So this on its own doesn't afford us something better than what we already had. The biggest capabilities that we get are when we look at rotation and scaling, because those are things that are not easy to do manually, but these two functions really make it quite easy for us. So if we go back to our push matrix here, we've translated the origin right to where we want to draw our rectangle, but before we draw it, we could also rotate the coordinate system, and that's going to rotate the rectangle drawn at the origin. So we can use the rotate function, and the rotate function actually needs to take an angle in radians, which sometimes isn't that convenient for us, but there is a radians function that takes a degree value and converts it to radians for us, which is quite nice. Now, if I wanted to have my rectangles maybe spinning, I would just need to have some kind of value that's changing each time they're in the system. So what I could use is I maybe use my value of steps. Right at the start it's 0, the next frame it's 1, 2, 3, and so on. And maybe I'll just scale it up by 5. So that would give me a 5-degree rotation on my first frame, a 10-degree, then a 15. And if I were to run this, we should see that we've got all sorts of rotations now happening. And we can kind of play around with those different factors. But it's something that's really easy to do if we use this transformations on the coordinate systems. But if we try to transform the object itself manually, it's actually quite difficult to do. Lastly, we should try experimenting with scale. Now, if you scale with a value of 1, we're going to see no change to our coordinate system. So values larger than 1 are enlargements, values between 0 and 1 are reductions. And I think actually for particles they really often look very nice if as they travel they also get smaller. So I'd like to scale to a smaller value. Now just like rotate, I can't just put a constant number in here. If I were to put 0.8, it will scale to 80% of its size, but it will scale each of them 80% of the original every frame, and it's not going to change. This would be basically the same as me going in and modifying my size value to a lower value. Instead, we want something variable here that's going to change over time. The farther it gets from the emission location, the smaller it gets. Now, we do actually have that steps variable still, right? It starts at 0 and it counts all the way up to 100. Now, that's not really the range of values we're interested in, right? Because we actually want to start at 1 and get closer to 0. But there's a very handy function actually called map that lets us take a variable and tell it the range of possible values. So I could say the possible values for steps are somewhere between 0 and 100. And then it will remap it to a new number range that we give it as our 4th and 5th argument. So why don't I just type it in here? That's probably the easiest. So I would say I want to use the variable steps, and its possible values are from 0, that'd be a floor value, to a ceiling of whatever lifetime is. In this case it's 100. And I would like you to remap that to a range from 1 to 0. So basically the higher it gets, the closer to 0 it will be. The lower it is, the closer to 1 it will be. I mean, we have a 1-to-1 mapping here. If it's 0, our scale will be 1. If we reach 100, our scale will remap it to 0. In between, it will pick that appropriate middle point. So if we were to hit run, we can see now that the objects are trailing off as they spin into the distance, and it's considerably more interesting a visual system than we had before. We'll have one more video here where we're going to look at abstracting with one more layer. Instead of building particles and storing on the list, we'll create a new object type called a particle system and see if we can create a number of systems at the same time.